Okay, so where we left off last semester was with drawing Lewis structures. Okay. However, in order to understand why we need this Vsepr theory in our lives, we have to understand like what's the weakness of a Lewis structure. Okay. So to do that, let's draw a Lewis structure of methane. Okay. So methane is just CH4. So how many valence electrons does carbon have?
4.
Okay, 4. How about hydrogen?
1.
1. And how many hydrogens are there?
2 or 4.
4. So how many total? 8. All right, so it's CH4. Which atom's going to go in the middle? Okay, C. And then we'll put those H's around it. All right, we started with 8. How many electrons did we use in those bonds? 8. 2, 4, 6, 8. Okay, so this is our Lewis structure. Okay. Now, here's the weakness of a Lewis structure. How many of you think that looks like a flat pancake, right? Like in real life, this structure would just be flat. Would you agree with that? Okay, so it turns out in real life, I'm going to use these balloons up here to show you. Methane actually ends up kind of looking like this in real life. Okay. So based off of your drawing on paper, does your 2D picture on paper look anything like remotely close to this?
No.
Not at all, right? So the problem with Lewis structures is they don't show us what molecules actually look like in the real world. Okay, they don't show us a 3D structure. So we use something called Vsepr theory to understand, well, what are the 3D shapes of molecules? All right, so first, Vsepr is just an acronym. You do need to know the acronym. So Vsepr stands for valence shell electron pair repulsion. So go ahead and write that down. And then you can write down my bolded words at the bottom. Okay. And I'm going to pause. I'm going to give you just a couple minutes to write it, and then we'll talk about what this means. So let's talk about like what Vsepr theory actually states. And it is literally in the name. So valence shell. What is a valence shell?
The outermost shell.
Okay, so the outermost shell of the atom. Okay. What's an electron pair?
A pair of electrons.
Good. Pair of electrons. And what does the word repulsion mean?
They repel each other.
Okay, they repel each other. Why would electrons repel each other?
Because they're the same charge.
Okay, they're the same charge, right? What kind of charge do electrons have?
Negative.
Negatives. And two negative charge, if we put them right by each other, what are they like naturally going to do? They're going to repel. Okay. So all Vsepr theory is, it is just this theory that says these electron like pairs want to be as far apart as possible. Okay. So the way molecules form their shape, it is to get those electrons as far apart as possible. Okay. All right. So to figure out the shapes of electrons, we're going to use that chart I gave you. Okay. And we'll go over the chart on the last slide. But the charts just show us the different types of shapes. So here are just some like names to get familiar with. So sometimes molecules are linear, so they're in like a straight line. Trigonal planar. What shape do you think trigonal is? Okay, triangle. And then what do you think planar means? It's flat, like it's all in the same plane. Okay. Tetrahedral is the shape of like a tetrahedron. Do you remember like learning that shape in geometry maybe? Okay. Trigonal bipyramidal. Again, what does trigonal mean? Okay, like a triangle. And then show with your hands, like, what's a pyramid? Like pyramid. So, like, bipyramidal is like pyramid on top, pyramid on bottom. So, the shapes, they are just explaining, like, just using, like, really simple geometry terms. Okay. When we look at the shape of molecules, we look at two different shapes. And, yes, you definitely need to write these ones down. Okay. So, the first shape is something called the electronic shape. And this one is going to include any lone pairs of electrons. Okay. So in the word electronic, do you see the word electron? Okay. So I remember this. So the electronic shape includes lone pairs of electrons. And then the molecular shape, only takes into account like the actual atoms that are bonded together. If we were to pretend that we could see molecules up close, like let's just pretend we could see molecules, do you think we'd be able to see those itty bitty tiny electrons? Okay. So I always think of the molecular shape. If we could see that small, it would be like, this is the one of like what you would see. All right, so we'll go over some examples, and I'm going to show you like what is the difference between the electronic and the molecular shape. Okay, so if you're not quite with me on this slide, that is okay. Be patient. All right, we're going to go through 3 different examples. I have pictures. I'm also going to use balloons, but I'm going to show you like what is the difference between the electronic and molecular shape. This top row is going to be the electronic shape. Okay, so it's going to include these lone pairs of electrons. The bottom row is just going to be the molecular. So the first one is methane. Again, I'm going to use the balloons to kind of help us visualize this. So methane's electronic shape is tetrahedral, which means it kind of looks like this, like a triangle on the bottom with one hydrogen sticking up. Okay. Does methane have any lone pairs of electrons? Okay, so its molecular shape is also tetrahedral. So if we could look at one molecule of methane, it would look like this. Okay. Next we have ammonia. So ammonia is NH3. So N would be in the middle, and these are 3 hydrogens, and then your lone pair of electrons is up here. Okay, so electronic shape is still tetrahedral. In real life, though, if we could see it, would we see that lone pair of electrons? Okay, so then molecular shape is if we just take away those electrons. Okay. So molecular shape is trigonal pyramidal. So trigonal means triangle, and what's a pyramid shape? Okay, so these would like point down a little bit. There's some limits to my balloons. And then last we have water, H2O. So if we include the electrons for water, it makes this tetrahedral shape. Okay. However, do we see these 2 lone pairs of water, or 2 lone pairs of electrons?
No.
Okay, so if we were to remove 2 of them, all we're left is with this, and we call this a bench shape. Does that kind of help make sense, the difference between electronic and molecular?
Yes.
Okay, electronic is important because even though we can't see those lone pairs of electrons, do they exist?
Yes.
Okay, so electronic is the reason why the like bond angles are what they are. Okay, so electronic is really determining like the angles in which these molecules form, and then molecular is important because do we see the lone pair of electrons? No, it's like the shape of what we would see. All right, so then today we're going to learn how do we know what the electronic and molecular shapes are. Okay, so this slide is my steps. So if you are a step person, write out these steps. And then on the next slide, we'll do 2 practice problems. Okay. So there's 4 steps to figuring out the shape. The first thing, you have to draw a Lewis structure. Okay. So we still have to know what it looks like 2D on paper. Okay. Then we're going to count the number of bonded atoms. And then we're going to count the number of lone pairs. And I'm going to add. When we count the bonded atoms and the lone pairs, it is only on the central atom. And I'll show you, we'll do some examples together. I will show you what I mean by this. However, add this part in your notes. Okay, this is important. So we only care about what's bonded to the central atom. And then finally, we'll use that Vsepr chart to actually find the electronic and molecular shape. We're going to do 2 examples together. If you haven't really been taking notes, is this the point where like you definitely need to do these 2 examples with me? Yep. Yes, you do. Okay, so we're going to find the electronic and molecular shape of SO3 with the -2 charge. Okay. So if you look at the steps, okay, if you look at the steps you just wrote down, what's step 1? Okay, you have to have a correct Lewis structure first. Okay, so the first thing we do when we draw a Lewis structure is, what do we count? Okay, valence electrons. How many valence electrons are in sulfur?
6.
Okay. What about oxygen? And how many oxygens are there? Okay, and then what does this little -2 charge mean? Okay, it gained 2 electrons, so you need to add 2 to your count. Okay, so how many total electrons are there?
26.
Good. Okay, 26. Now, which atom is going to go in the middle? Okay, and then we'll draw the O's. Okay, we started with 26. How many electrons did we use in each single bond?
6.
Okay, 2, 4, 6. So how many electrons are left?
20.
I got you. Okay, 20. Let's just start with this oxygen. How many electrons does it have here? 2. How many does it want to have total? 8. So how many dots do you have to add? Okay. And are all 3 oxygens going to be the same?
Yes.
Okay. So I'm going to go ahead and give all of my oxygens 6 dots. Okay. So then how many electrons are left over? 2. Where do those final 2 electrons go? Good. Sulfur only has 2, 4, 6. And how many does it need? 2 more. Good. Okay. So step 1. You have to have a valid Lewis structure. If you have an error in your Lewis structure, are you going to get your shapes wrong?
Yes.
Yes. So make sure you take your time on your Lewis structure. Okay. Now, we're going to count the number of bonded atoms in lone pairs. When we do this, it is only on the central atom. Okay. So how many atoms are bonded to sulfur? 3. 1, 2, 3. Okay. And then when we count lone pairs, again, it's only on the central atom. So how many lone pairs are on sulfur?
1.
Okay, 1. I'm going to just like draw it in yellow. Okay, so that itself is a lone pair. Again, how many electrons make up a pair? 2. So don't be confused. Just because it's 2 dots, it's still just 1 pair. You with me there?
Yeah.
Okay, so now we're going to find the electronic shape. I'm just going to say ES for short. And we're going to find the molecular shape, okay, MS for short. And the way we're going to do that, we're going to use this chart. Okay, so pull up your Vsepr chart. Okay, and let's just kind of look at the columns. So the first column is total domains. That we're not really interested in. Okay. Next, generic formula. You could just make sure your formula matches the generic formula. That's a good way to check. Okay. Picture is going to show us like what does this look like in real life. Okay. And then that fourth column is the bonded atoms. You with me there? Okay. That's the important one. So in this drawing, how many atoms are bonded to sulfur? 3. Okay. So you're going to go down until you find 3. But then go down a little bit further. Do you see 3 again? Okay. If you look on the back side, do you see 3 again? Okay. So notice numbers pop up multiple times. So you also have to use the next column of lone pairs. Okay. And again, when it's lone pairs, do we care about all these lone pairs on the oxygens? Okay. Nope. We only care. Make sure you're giving your attention up here. So we only care about the lone pair on sulfur. So how many lone pairs does sulfur have? 1. Okay. So you need to match your columns till you find 3 and 1. Okay. So go down till you find 3 and 1. Okay. All right. Did we find it? Okay. One thing I want to point out. I always do electronic shape first. And when you do like this practice chart today, electronic's going to come first. Okay. However, when you look at your chart, which shape does it give you first? Molecular. So we're just going to switch them like in our heads. Okay. So it says molecular shape, and then it says electron geometry. Is electron geometry the same thing as the electronic shape? Yes. Okay. All right. So if you go to 3 and 1, what's the electron geometry or the electronic shape?
Tetrahedral.
Okay.
I don't know how to say that word.
Tetrahedral. Okay, so electronic shape is tetrahedral. And then what's the molecular shape?
Triangular pyramid.
Good. Okay, so the molecular shape is trigonal pyramid. Let's do the same thing for xenon tetraiodide. Okay. So what's the first thing you need to do? Okay, draw the Lewis structure. So what do you need to know to be able to draw that Lewis structure? Good. Valence electrons. How many does xenon have? Good. How many does iodine have? 7. And how many iodines are there? Okay, so how many total? Okay, 36. Which atom is going to go in the middle? Okay, so we'll put xenon in the middle. Then we'll put our iodines around it. And then this one's going to be a really good example of why you need to keep track of your electrons. So you started with 36. How many have we used in the single bonds? Okay, 8. 2 each. So 2, 4, 6, 8. All right, what's 36 minus 8? Okay, so we have 28 more electrons. I'm just going to start with this iodine. So this iodine has how many here in the bond?
2.
2. How many total does it have to get to? 8. So how many dots do you have to give it? Okay. Are all 4 iodines going to be the same?
Yes.
Okay, so I'm going to go give each iodine 6 dots. And then what is 6 times 4? Okay, so we have 4 electrons left. Okay. Does iodine have a field octet? Okay. Does xenon also have a field octet?
Yes.
Okay. Can we just pretend that these 4 electrons don't exist and not put them anywhere?
No.
Okay. We maybe did 1 or 2 examples of these last semester, but I just wanted to highlight it again. You have to place them no matter what. So that means one of these atoms gets to break the octet rule. Is it going to be the central or an outside atom? Okay, so if you have extra electrons, you have to draw them. And you'll put it on the central. And they're going to be in pairs. So you can just put a lone pair on one side of xenon and a lone pair on another side. Okay. But this is a really good example why you need to track your electrons. If you didn't have these lone pairs here, you wouldn't end up with the correct shapes. All right, so now we're going to find, I'm going to say ES for electronic shape, MS for molecular shape. Okay. What resource are you going to use?
That too, but.
Okay, you're going to use your chart. So the first thing you're going to count is bonded atoms to the xenon. So how many atoms are bonded to xenon? Okay, so 4. And then you're going to count lone pairs. Are we interested in every single lone pair in this entire Lewis structure? Okay, which lone pairs do we care about? Okay, so how many lone pairs are on xenon? 2. Okay, so go to find 4 and 2 on your columns. Okay, did we find 4 and 2?
Yes.
Okay, what's the electronic shape? Okay, good. So we call this one octahedral. And then what's the molecular shape? Perfect, square planar.